Our next speaker, Jae-Sung Oh, will be telling us about towards Butler's conjecture.
Oh, I think it's working.
Yeah. Awesome.
Thank you for the introduction, and thank you all for being here. So it's my fourth time attending FPSAC, but it's my first time attending in person. So I'm very happy to give a talk, seeing your faces, and thanks for giving me a chance to give a talk here. So I'm gonna talk about toward Butler's conjecture, which is joint work with Dong-Young Kim and Seung-Jin Lee in Seoul National University. And thanks for the wonderful talks, previous talks by Jonah and George. Yeah, they didn't actually give a precise definition of Macdonald polynomial, but I'll skip it anyway. So, so you can just think of Macdonald polynomial as a Qt analog of Schur function, and that's all you need. So, as Jonah already mentioned, one of the most important problem arising in the Macdonald polynomial is Macdonald positivity conjecture, which is eventually proved by Heyman. And it says that the Schur coefficient is a polynomial in Q and T with non-negative integer coefficients. And we call these Schur coefficients as a modified Qt Koska polynomials. And he uses a geometry of Hilbert schemes to prove this Schur positivity, but we lack of a combinatorial formula. So it is a major open problem to give a combinatorial interpretation of this Qt Koska polynomial. And I'll introduce one observation that might hint us to give us such formula. So, an observation. So, let's say T mu is a product of Q to the coarm, T to the coleg. So, for example, if you have a partition 2, 2, T lambda is a product of 1Q, T, and Qt. So, it's Q squared, T squared. And T mu here is Q times T to the third. And if you write down the Schur expansion of these two partitions, one you can observe is that, I mean, if you order the monomials properly, some of the monomials are the same. So we are connected with red edges. And the other coefficient, the other monomials, they have ratio Q over T. Or you could just say they have the ratio T lambda over T mu. And this pattern or this phenomena was observed by Butler. So in general, you can think of like this partition in the blackboard here. So starting from a big partition nu, you choose two corners and remove one corner to obtain lambda and remove the other corner to obtain mu. And in that case, you can expand Macdonald polynomial. Like A is the same, and the other parts, they have ratio T lambda over T mu. So Butler actually conjectured that this A part, so A can be obtained by this divided difference, and I'll denote it by I lambda mu, and this I lambda mu is actually Schur positive. So, and I will call this I lambda mu as a Macdonald intersection polynomial. And starting point of our project is to give a combinatorial formula for this I lambda mu, but we don't know any Schur positive combinatorial formula for the original Macdonald polynomial, so we kind of hopeless. But the good thing is we know the F expansion. So there is so-called Heyman-Hagelin-Lohr formula, which is mentioned in the previous talks. So for a filling W of a partition mu, we say a pair of cells located like this or this, with the filling A is bigger than B, then we say those pair of cells is an inversion pair. And we say a cell is a descent if the filling of the cell is bigger than the filling of the cell right below it. And this is not a standard notation, but let me define HHL stat to be the Q to the number of inversion pairs times the product of Q to the minus arm, T to the leg plus 1 over all distance. And the celebrated Hagelin-Heyman-Lohr formula states that the Macdonald polynomial is just a generating function of HHL stat times f of inverse descent, where f is Gessel's fundamental quasi-symmetric function defined in this fashion. Okay, so if you want to expand H22, so Macdonald polynomial of 2, all you have to do is write down all 24 permutations and write down the inverse descent and HHL stats like this, and take sum of all like stat times f of inverse descent. And you can naively hope that this HHL formula directly give us way to, give a combinatorial formula for the Macdonald intersection polynomial. So, but this is not the truth. So you can hope that for each permutation, the stat of 2 and 2, may have ratio 1 or T lambda over T mu, but if you check this, you can see that there is some other patterns like that I write it in the black. So we somehow construct a bijection. We need to construct a bijection to swap these orders somehow. And that's what we did, and to explain our works, I have to introduce some notions. So a field diagram is a diagram with a function f, which is defined on the cells, which is not the bottom cells. And we will draw a field diagram like this fashion. So draw a diagram and put the value of the function in each cell. So alpha, beta, gamma, and delta are the value of the function f. And for a filling W of D, we define stat of a field diagram, just like we did in the where we defined HHL stat. So stat df over filling W is q to the number of inversion pairs times the product of function fu over all descent. So recall that HHL stat was defined in this fashion, so we kind of replace this q to the minus arm, t to the leg to an arbitrary function. And we define in a similar fashion to HHL formula, we define a Macdonald polynomial of a field diagram as a generating function of stat times f of inverse descent. And since, Macdonald polynomials are the basis, but we have generalized it to field diagrams, so it's a lot more Macdonald polynomials now. So there should be a relations between them. And sometimes you have two field diagrams which have the same Macdonald polynomials. So the first instance is a cycling rule, which is very easy. So for instance, suppose you have a field diagram like this, and you move the first column all the way to the right and place it one row up. Then it is very direct to see that their Macdonald polynomials are the same. So you can check that inversion pair is not changing and everything. Descents are the same. And the second instance of like two field diagrams have the same Macdonald polynomial is quite complicated, but we prove it in our paper, and we call it column exchange rule. And suppose you have two field diagrams which are identical except for these two columns. And you obtain the second one by exchanging these two columns. But you have to be careful. You have to change this value of the function q alpha to alpha here. So if you have two field diagrams like this, we can construct a stat and inverse descent and content preserving bijection. So since Macdonald polynomials are generating function of these two stats, so in particular we can say that these two Macdonald polynomials are the same. Okay. And to give a combinatorial formula for the Macdonald intersection polynomial, we start by two partitions like this. So like these two partitions, lambda and mu. And if you think of how we obtain these two partitions, they are identical as a partition, except for two columns, like I marked in blue and red here. So we apply the column exchange rule to move these columns. We have to apply column exchange rule again and again to move this blue column all the way to the right, this red column all the way to the right, all the way to the left, and do the similar thing for this. And for these two field diagrams, you apply cycling to obtain the final field diagrams. And what we can prove is that these shaded region, shaded parts are identical, not just as a diagram, they are identical as a field diagram. So their function, like there should be a fielding function here, so these are identical. So in a sense, to obtain a combinatorial formula for the Macdonald intersection polynomial, since these parts are identical, all we have to analyze is these two columns. So we have to analyze only this part. And what we have done is we have characterized a class B of permutations, and we have constructed a bijection zeta. And this permutation class and bijection zeta satisfies if you take the ratio of the stat of these two final field diagrams, then the ratio should be 1 if the permutation is in the class B. And otherwise, the ratio of it is T lambda over T mu. This is the exact situation that we wanted. And of course, we have to check the inverse descent is preserved. So this is how we proved combinatorial formula for I lambda mu. So I lambda mu now can be expanded as a generating function of stat times f of inverse descent over all, this B lambda mu comes from the B. So B lambda mu over all permutations that sits inside B lambda mu. And we name these permutations as a Butler permutations. Okay, so this is how this is sketch of the proof how we obtain the combinatorial formula. And the original Butler's conjecture concerns about the sure positivity of this Macdonald intersection polynomial. So we have some partial progress in that direction. So same situation, and if the mu minus lambda is in the first or the second row, so this is a corner. So if we choose a corner from the first or the second row, then the Macdonald intersection polynomial is sure positive. So that is one thing we proved. And without any conditions on the corners, we can prove that Macdonald polynomial is Macdonald intersection polynomial is sure positive if we specialize t equals to 1. Okay? And this is what we have proved for sure positivity. And and for the remaining few minutes, I would like to talk about motivation behind it, motivation to study the Macdonald intersection polynomial. So this comes out in the previous talks. So Garcia and Heyman defined a vector space, V mu, that sits inside this polynomial ring of two sets of n variables, so x1 through xn, y1 through yn. And this V mu is a bigraded SN module, and the name is Garcia-Heyman module. And they conjectured that the character of this Garcia-Heyman module is the Macdonald polynomial. And Heyman eventually proved this, thereby proving the Macdonald positivity conjecture, because since Macdonald polynomial comes from a genuine SN representation, so it should be sure positive. And in 1999, Francois Bergeron and Garcia, they studied not just a single Garcia-Heyman module, they studied tuples of Garcia-Heyman module. So in the Butler situation, we took two corners, right? And we can take k corners, and we obtain subpartition mu1 through mu k by removing each corner. So mu1 through mu k are a partition whose size is 1 less than the partition nu. And Garcia and Bergeron and Garcia, they conjecture that the intersection of those k Garcia-Heyman modules, the dimension of it is n factorial over k, and the graded Frobenius character, where I denoted by I mu1 through mu k, can be computed in this fashion. And this, in particular, generalized the Macdonald intersection polynomial that I mentioned in the Butler's conjecture. So we name this symmetric function indexed by k partition also by Macdonald intersection polynomial. And this is the reason why we named it Macdonald intersection polynomial, because it comes from, conjecturally comes from the intersection of Garcia-Heyman modules. And This is not in my extended abstract, but I want to advertise my recent result, which is on arXiv since June. So we have studied more properties of these McDonald intersection polynomials, and we proved that if you skew this McDonald intersection polynomial by some en, by en with n is large enough, then you get some kind of vanishing properties. And if you skew this by the appropriate e, so en minus k plus 1 perp, then what you obtain is a scalar times character of diagonal coinvariance. And we proved the B in an algebraic fashion, and we also proved that we do the same thing, that then what we can obtain is a so-called shuffle formula. So this is a generating function over parking function. And the thing is, if you combine B and C, this is the theorem, shuffle theorem, which is proved by Carson and Mellit. So we kind of gave an alternative proof of the shuffle theorem. And final remark is that, original McDonald polynomials, if you specialize Q and T equals to 1, you have a very easy symmetric function, so h1 to the n, right? So you can do the same thing for McDonald intersection polynomial. And if you specialize Q and T equals to 1, what you obtain is nice H expansion, which has signs in it, and there's a typo, so this mu is lambda. So that involves signs, and that involves Kravar's number, which counts the non-crossing set partition of this type, and there's a H here. So we somehow obtain this nice H expansion for this McDonald intersection polynomial at Q and T equals to 1. So if we assume the science fiction conjecture, this McDonald intersection polynomial should be sure positive because it comes from a SN representation, but it may be hard to give a sure expansion or prove the sure positivity. But if you specialize Q and T equals to 1, it should be, it may be easy. It should be easier. But even though we have this nice H expansion, we don't know how to prove the sure positivity of these symmetric functions, or we don't know how to give a monomial positive expansion of this symmetric function. And I think that might help us to understand more about this McDonald intersection polynomial. And so we have studied some facts about Butler's conjecture, and like the shuffle theorem miraculously comes up. So, and this interesting combinatorics comes up when we are studying science fiction conjecture. So I would like to encourage you to study more or explore more about the science fiction conjecture. And that's all for our talk. Thank you.
Are there questions?
Could you go back to the previous
Here?
Yeah, so I'm confused. Maybe I missed something. There's no dependence on mu1 through mu k?
No, so there's a dependent, number of ones in the tail, but there's no dependent of the shape mu1 through mu k.
So what is the number of ones? K, is it?
No. So number of ones should be n. Mu1 through mu k are partitions of n, okay. So the degree should be matched. So yeah. Oh yeah. These mu1 through mu k should be like obtained in this fashion, like removing corners, right? Yeah.
Yes.
Yeah. So I'm kind of interested in this class of permutations you defined and named the Butler permutations. So those are new, I guess.
Yeah, I don't know for sure, but I believe
right.
Those are new. And
yeah. And so have you done anything with figuring out like any of the properties of any sort of combinatorial properties of these permutations?
Yeah. Oh, So what he asked is if this Butler permutation is new class of permutation, and if there's a combinatorial properties, of these Butler permutation, and I think we try to find out, and we find out that we did some calculation for inversion generating function and major generating function, but I personally cannot find any interesting stuff. But if you do descent generating function, so number of the descent, then you somehow obtain something like this. So if you expand like the generating function of q to the descent, it gives like q to the k and Eulerian number, right? The number of, and if you do the same thing for Butler permutation, then what you obtain is something like En minus 1k times k q to the k. So, yeah.
Further questions? Yes?
So the leading coefficient in your H expansion seems to be the first two terms seems to be the Kaplan numbers.
Yeah.
Is that also?
Yeah. So, oh, yeah. So she's asking if in this expansion, the first leading term, the coefficients of the leading terms are 1, 1, 2, 5, 14, which is our favorite sequence. So these are Catalan numbers, and that is true, and it is true in a more powerful sense because this, if you think of how you taking this E perp, then this taking E perp, you gives a shuffle theorem, so it should involve the Qt Catalan numbers. So actually, Qt Catalan numbers sits inside this first, the top term, coefficient. But so the coefficients, if you expand it in Q and T, the coefficients of these top H's are positive, but it's a lot more messy in like other H's. So yeah.
One final question? Yes.
So the other numbers, they seem to be the faces of the associahedra.
Yeah. So it comes from Kravers. Oh, yeah, sorry. So the other coefficients like 551, 1421, 361, these are, he asked if these are the number of faces of the associahedra, and these are the Kravers number, and Kravers number counts the number of non-crossing set partition, and I believe there is a way to, see the bijection, between those stuff.
Okay, let's thank Jae-sung again.
Thank you.